You click to see the largest planet ever found.
NASA's Kepler Space Telescope takes the search above Earth's atmosphere into space.
So here's the twist. At a certain size, a planet starts to look suspiciously like a failed star. Where is that line, and does this giant cross it? In the next minutes, we'll unpack the mass, radius, and density that push it to the edge of brown dwarf territory. Stay with me as we trace how astronomers actually detected it and why its sheer scale forces us to question what the word planet really means. You know Jupiter is big, but here's the riddle. Why do astronomers pause when they find something with dozens of Jupiter's mass that still measures about the same size across? The hesitation starts with definitions. The IU's checklist works for our solar system, not for thousands of exoplanets orbiting other stars. So researchers lean on 3 clues instead: how heavy it is, how it formed, and whether it ever had the internal heat to briefly fuse deuterium. That last bit creates the mess. Around 13 times Jupiter's mass, the pressure inside can light deuterium for a short phase. Sounds like a clean cutoff, but it isn't. Some objects below that limit form the way small stars do, collapsing directly from a cloud. Others above it live in tight orbits, carry signs of disk-borne origins, and look like oversized planets. The line blurs because the key is ignition, not the badge on the hood. Think of it like a car. Mass is the ignition key. Radius is the body style. Turning the key, deuterium fusion, depends on the engine under the hood, not the paint job. You can have 2 cars the same size. One roars to life, the other doesn't. In space terms, 2 worlds can have similar radii, but only one reaches the conditions to briefly fuse deuterium, and even then it's a short-lived flame that fades as fuel runs out. Even that ignition key isn't fixed. The threshold sits near 13 Jupiter masses, but composition nudges it. Add helium and the object gets denser, raising core pressure at a given mass. Change the heavy element content, its metallicity, and you tweak opacities and cooling, which shifts when and whether deuterium lights. A slightly helium-rich, metal-rich object could spark fusion at a bit lower mass, while a metal-poor one might need a little more heft. Those small differences ripple into classification. Here's where radius plays a trick on intuition. Gas giants don't keep swelling as you add mass. Past a point, gravity wins and compresses the interior. Electrons get squeezed into a degenerate state that resists further compression only weakly. So many superjupiters hover near Jupiter's radius, some even a tad smaller, while their mass climbs steeply. Heat from a tight orbit can puff a planet's outer layers, inflating the radius, but heavy ones often fight that inflation with sheer gravity. The result is a wild range of densities that breaks simple expectations. Borderline examples make the point. Pat, P, 2b packs several Jupiters into a radius not much larger than Jupiter's and orbits on an eccentric track, giving it a hefty mean density. Perot, 3b sits in the gray zone with a mass creeping toward the deuterium line and a near-Jupiter radius, yielding an iron ball density. Then there's Kepler, 75b, also known as KOI, 889b, which loads mass onto a compact frame and comes out far denser than everyday metals. Meanwhile, some hot giants at lower mass swell into low-density worlds with interiors more like stiff foam than steel. Same ballpark radius, opposite internal stories. So the label isn't a one-lane road. It's a triangle. Mass points toward gravity's pressure, radius hints at the envelope's response, and formation tells you whether the object grew from a disk like a planet or collapsed like a small star. Deuterium fusion sits in the middle as a messy rule of thumb. Useful, but not final. Ahead lies the case that presses the boundary hard. A near-Jupiter radius, an extreme mass that drags its star around, and a crushing density you can't reconcile at a glance. The question is, how did astronomers spot a heavyweight like that without ever resolving its disk? What tiny signal gave away a world that hides in glare, yet throws its weight around like a wrecking ball? So what tipped off observers? A tiny blink in starlight, or a star yanked back and forth so hard you could clock it like a speeding car? The giveaway came from both. Transit photometry shows you size by how much light the planet blocks, while radial velocity tracks the star's wobble to reveal mass. Put them together and the math hands you density. And with density, you can tell if you're dealing with a puffy lightweight or a compact heavyweight pushing the planetary limit. A transit alone can be misleading. A dip of about 1% hints at a radius close to Jupiter's, because that drop scales with the square of the size ratio between the world and its star. But if the radius barely grows while the mass skyrockets, the shallow dimming hides a serious punch. That's where radial velocity steps in. A star that lurches by hundreds of meters per second per orbit is not being nudged by a run-of-the-mill hot Jupiter. It's being towed by something with tens of Jupiter masses, packed into nearly the same footprint. Think through a typical catch. Surveys flag a repeating 1% dip on a bright, sun-like star. The period is a few days, so the planet is close-in and hot. Follow up with a precise spectrograph shows a clean sine wave in the star's velocity, swinging by, say, 500 to 1,000 meters per second. That amplitude, tied to the known orbital period and the star's mass, solves directly to a companion in the tens of Jupiter masses. Transit depth fixes the size near Jupiter's radius. Divide mass by volume, and you get a density that outmuscles steel by a wide margin. That synergy of survey and precision work is the engine behind these finds. Wide-field photometric campaigns like WASP, HATNet, KLT, and TESS watch thousands to millions of stars for tiny periodic drops. When they flag a candidate, high-precision spectrographs, HARPS, HIRES, SOFI, Espresso, take over, measuring Doppler shifts to a few tens of centimeters per second on quiet stars and well below a meter per second in ideal cases. For borderline giants, you don't need that extreme floor. The signal is loud, but you do need clean, stable measurements to rule out blends, stellar activity, or eclipsing binaries masquerading as planets. Among confirmed transiting planet-class objects, one sits at the top in mass while still carrying the planet label, CoRoT 3b. It orbits an F-type star, circles in just under 4 days, and bakes at an equilibrium temperature of roughly a couple thousand Kelvin, depending on albedo and heat redistribution. Its measured mass lands near 20+ times Jupiter's. Its radius is only a few percent larger than Jupiter's, and the density stacks up at well over 10 grams per cubic centimeter. That's denser than most common metals you deal with, more like the squeeze you'd expect inside a white-knuckled anvil than a gas ball. Those numbers give clues to its past. The host star's metallicity hints at a disk rich enough to grow massive cores and feed runaway gas accretion, but pushing to several tens of Jupiter masses strains classic core accretion models. Its tight, short-period orbit points to migration after formation, likely through disk interactions or dynamical kicks followed by tidal circularization. On the other hand, a star-like collapse pathway could make an object this heavy more naturally, then leave it in a close orbit if the system dynamics shuffled it inward early. So why keep it on the planet roster? Transit and RV data show no signs of sustained deuterium burning. Models say any brief deuterium phase would have faded quickly, and its placement in a standard hot Jupiter-like architecture, short period, transits, a single dominant companion, matches how we catalog planets from surveys. You now have the toolkit, radius from the dim, mass from the wobble, density from both, to see why the label is a debate rather than a verdict, and the next step is deciding which boundary matters most. The largest planet forces you to split your thinking. Its mass leans toward the brown dwarf neighborhood. Its size stays stubbornly Jupiter-like, and the real clue lies in how it is assembled and whether it ever flickered with deuterium burning. That's why one number never tells the story. When a new candidate appears, scan the trio, mass from the wobble, radius from the dip, density from both. Then ask the fusion question, did it light deuterium, and for how long? That reads the frontier. Now push it forward. What happens when surveys find one even heavier, cooler, and ancient? Maybe the word planet bends again.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery,